This video is a continuation of video tutorials on civil engineering materials lab experiments. I am Usman Javed. I will be teaching you different lab experiments of civil engineering materials. So basically, there are two types of there are two methods used to calculate the fineness of a cement. One method is like by calculating the Blaine Air Permeability apparatus, which is so sophisticated apparatus which gives the value in terms of some fineness and surface area. On the other hand, you have a method using the sieve method of you calculating the surface area of a cement, in which you can use the different types of sieves. So according to ASTM C430, you can use the sieve number 325, which has a particle which has a sieve opening of 45 micron, which is valid till weight. On the other hand, ASTM C786 suggests to use the sieve number 200, which has a sieve size of a 75 micron. You can use sieve number 100. So ASTM C430 is replaced by the ASTM C786 due to the reason that the ASTM C786 used the multiple sieves, sieve number 200, sieve number 100 for calculating the fineness of a cement. So the catch is the cement particle size is around average particle size of cement is around 30 microns. So you cannot use the cement sieve with the opening size of more than 45. So ASTM has replaced this standard ASTM C786 with the ASTM C430. So in this slide, you can see the particle size of a cement comparison with other SCM supplementary cementitious materials. Here's a fly ash. Fly ash particles around fly ash is basically formed in kilns, which are extracted electrostatically while the burning of a fuel in kilns, in a type of a furnace or a kilns used in industries. So the fly ash particle is spherical because of the same pressure the fly ash particle is being exposed to in the kiln, so the particle size is too much around. So the particle size of a fly ash is in comparison with that of a cement. If we talk about the silica fume is nano based, nano micro uh, particle size it contains. The particle size is too much small, it contains a higher amount of a silica. And on the other hand, ultra fine fly ash have a particle size much lesser than a nominal fly ash. So basically this is a comparison between the supplementary cementitious material with that of cement. So fineness is important for having a quick reaction and efficient hydration reaction in concrete. So we have two standards which talk about the fineness using the sieve method. So according to ASTM C43, you can use the sieve number 45 or sieve with a opening size of 45 micron. So you can see that you first have to um, make sure that the sieve number 325 must be clean. It do not contains the very fine particles within the openings. You must have to clean it before the use. So you will find the fineness of just standard specimen. For example, you have a standard specimen with a known fineness, then you will use to have the fineness using that sieve number 325. So what is the procedure to find the fineness using sieve? There is a dry and wet procedure. In dry procedure, you just pour the specimen. So specimen size must be 1 gram of a specimen would be used to pour onto the sieve. Rub the sample so that the finer particle size would be the would leave the sieve below. After a while, you will perform this dry procedure, and you will find the percentage retained on the sieve number 325. On the other hand, you can perform another method of a wet sieve method. You place a specimen on the sieve and you make the jet of water that force the particles to move into the move through the opening of a sieve. So after 10 to 15 minutes, you will get the some substrate retained on the sieve. You will calculate the weight after the oven drying for 24 hours. In this way, you can find the you can calibrate your sieve. The percentage, um the percentage which we will get, like for example, I have some standard specimen which have a fineness of 12%. I mean 12% retained on a sieve number 100, sieve number 325. Then you will use to have these tests repeated on that standard specimen. You will get the 9.3 value. So 9.3 value means it have a correction factor of 31.2. There is a variation between this is a variation of a 2.9 percent. So 2.9% variation means that you will apply the correction factor of a 31.2 into your result. Basically, this is a calibration of a sieve. So for performing the fineness using the sieve method, you will take the cement sample, 1 gram of a cement sample, and place it over the sieve number 325. You will use a water jet to allow the particles to pass through the sieve number 325 openings, and after 10 to 15 minutes of this operation, you will keep your substrate on the sieve number 325 into the oven for 24 hours and record the weight and determine the weight loss. Uh, the weight retained on sieve number 325 must not exceed 10%. The 10% value suggests the fineness of a cement, a good fineness or adequate fineness of a cement. So after calculating the value, you must add the 31.2% of a result into your sample, so that you can get the accurate result. So this is a simple way to calculate the fineness using the sieve method. Now we have a cement fineness test. We can find the fineness of a cement by two methods. By Blaine Air Permeability apparatus, which gives you the fineness value in terms of centimeter square per gram or meter square per kilograms. And on the other hand, you have another method which is basically obsoleted in ASTM standards, which is, so here's an apparatus. It is known as the Blaine Air Permeability apparatus. If you see that it comprises of a manometric tube which contains a manometric fluid. It is a U-type manometric tube. At the top of manometric tube, you have a cell in which your sample is kept. If you can see that the cell contains the sample, cement sample, which is being surrounded by the um, two filter papers at the bottom and top respectively, and the cement sample is laid upon the perforated tube upon which the air can be passed through it. Now the cement sample is confined by some plunger from upward direction, so that it can have a fixed volume of a cement by specifying the constant porosity, the specified porosity. In the YouTube manometer, you can see that there are different type of marking. There are 4 marking points are mentioned. The top and bottom marking point is basically reference points. For the top point, when your manometric liquid reach at a point 1, it is basically a reference that gives you a warning that you must be cautious to record the time when the manometric liquid reaches up to the point 2. The moment the lower meniscus of a manometric liquid hits the point 2, you just start the stopwatch and record the time between 2 and 3 point. Basically, the time which is required for the manometric liquid uh, to travel between the point 2 and 3 is basically the time in which the air is passed through this cement sample. We will discuss in a and later that we will get a clear idea about it. So it also is attached with a rubber bulb, in which you just apply the negative pressure in the YouTube manometer so that your manometric fluid can be sucked up, and when you release the rubber bulb, the air is tend to pass through this perforated tube and then the cement sample, and then pass and then evolve into the atmosphere. Gradually, at the same time, your manometric tube liquid will be dropped due to the perforation of air from this perforated tube. So you record the time between 2 and 3 point, and you will get the fineness based on their delayed time between 2 and 3 point. Basically, the idea is higher the surface area of your material, more will be the delay time between these 2 points. Lesser the contrarily, lesser the surface area of a material, smaller will be the lag time between 2 and 3 points. So we can get an idea about it by this video tutorial, in which you get the basic theme and how to do the calculations of this experiment. Basically, this is a cement column, a cement confined column, which is being confined by the plunger on the one hand, on the perforated tube on the other hand. The air is passed through this cement column. You just note down the time required, the specific portion of air to pass through this cement column. That time would be recorded as time t on your stopwatch. While this test would be conducted at 20 degrees Celsius, and your relative humidity would be around less than 65%. First, you insert the manometric tube into the manometer by injecting it using some syringe. It's a perforated tube which basically lies at the bottom of the cement cell, and this is basically a plunger which is just used to insert into the into this tube. These are the equipment that you need. You must have a manometric. You must have a manometric liquid. Then you have a syringe upon which, with the help of which, you can insert the manometric fluid into the YouTube manometer, and then you have a filter paper. In this experiment, first you will have to calibrate your equipment using some standard powder, so that you can have properties of, or you can say the time lag or a surface area of you have to find the K value of your apparatus, that is constant value. Basically, K value is the ratio between the standard specific area and your specimen specific area, so that it can give an accuracy regarding this test. This is automated Blaine Air Permeability apparatus, in which is used to record the time automatically between the column of a manometer. This is a procedure how you can insert the manometric fluid into the YouTube manometer. Basically, these are the points that I have mentioned earlier. This is a top mark. This is a starting point at which you start your time, and this is the stopping point that you will stop your stopwatch between. This is a reference point of a. This is a reference material. Reference materials have a density of about 2.65 gram per centimeter cube and a porosity of 0.5. First, you have to find K value of your reference, K value of your instrument, so that you can find the accuracy about your equipment. The first step is to find out the volume of the column in which the cement would be inserted in. The cylinder in which the cement has to be inserted, below which there is a perforated tube, Above the perforated tube, you first place the filter paper so that cement cannot pass through this perforated tube. Then you insert the cement. Then you insert the your sample, and then your filter paper again. In order to find the volume of this cell, you need a vernier caliper by which you will find the uh, depth of this um, column, which is assigned as a J. After calculating J, you will find the depth of a plunger. It's a depth till the plunger reaches into the um, into the cell in which the cement is present. So this is the formula to calculate the volume of a cement. Basically, this is a pi r square, which is the area multiplied by the depth of a column. Area multiplied by depth equals to volume, and 1000 is a conversion factor from millimeter cube to centimeter cube. So you can find the volume. These are the prerequisite steps. Basically, these are the prerequisite steps to find out your how much the mass of a sample you have to required in order to find out the surface area. So you will find the volume by inserting these values. Basically, this is the depth of a cell, and this is the depth of a plunger. If you minus this, you will get the height of a cement sample or a depth of a cement sample in the cell. This is the inner dia. By this formula you will get the area, cross-sectional area multiplied by height. You will get the volume. This is the conversion factor. This is a formula to get the mass, how much mass you have to require in order to calculate your surface area. If you put the larger mass than the required, then it will not calculate the desired surface area, because it contains a larger amount of a mass than it has to be. This is a formula in which the E is a porosity of a reference material. Reference material porosity I have mentioned earlier that it's 0.5. It's a density of a reference material which is around the 2800 kg per meter cube, and you will get the mass. Volume is already been calculated. 2.65 is a density of a reference material. You can see that the reference material has a density of 2.65 and porosity of 0.5. So after calculating the volume, you will now calculate the K, the value of K. For this purpose, you will insert your reference material into the cement cell, and which is surrounded by the two filter papers, and you will then insert the plunger upon it. Basically, this is a mass that you just have calculated before of the reference material. 2.56 was the mass which has been calculated before of the reference material. Then you will insert the plunger and compact it well, so that the air particles present between the cement particle, as the cement grain size is too much small, so there might be some air present in the cement particles that must be released by inserting the plunger and rotating it. Then after the placing the cell onto the top of your device, you will just press the button so that it automatically sucks the manometric fluid, and the timer would start between these 2 points automatically. You are seeing that the manometric fluid is dropping with some constant rate, and this is basically a start point. Machine is automatically started. After reaching the finish point, it will be automatically stopped, giving you a time between these 2 points. So you have a stopping point. The liquid has been reached. It's 60.42 seconds to calculate the constant of this machine. S naught is a specific surface area of a sample, that is reference sample. You have a rho naught, which is the density of a reference material that we have from the manufacturer. The S naught is being calculated now. E naught is provided by the manufacturer of the reference material, and eta naught is basically the air viscosity, which is constant. T naught is the time between these 2 points of the reference material. In this way, you can calculate the value of K, which is a constant. You will find the value of K for the reference material. Make sure that you repeat this experiment for 3 times to find an accurate value by taking the average of a 3, so that there would be a minimum error or some minimum error of a repeatability. Now it's a time to calculate the surface area. Now you have a reference material. Now you have a value of K for your reference material, and you will, by the help of which you will find out the surface area of a cement. You have to repeat the process of finding the surface area. Finding the time lag between the 2 points of a manometer by repeating the same procedure that you have done for the reference material. Basically, this is the mass to calculate the your cement sample. Basically, cement have different density than your reference material, so the mass of a reference material would be the different than the mass of a cement used for this volume. So you will put the density of a cement, which is 3.14. Volume would be the 1935 centimeter cube. Porosity of a cement you will using would be as specified by your manufacturer. So by calculating the mass of a cement, which is around 2.7 something, you will get you will just pour the cement into this cell and insert the plunger to release any air entrapped between the particles. After repeating the same procedure, you will get the time T, and using this time you will be able to calculate your specific surface area of sample. This is basically the formula that you will be using while you're calculating the specific surface area of a cement, which is K divided by rho. K is a constant of a reference material. Rho is a density of a cement. T is a time lag. Eta is basically the air viscosity. You have calculated the K earlier, which is 18.16. Porosity is around 0.5. It's porosity of a reference material, keep in mind. T is the time required for a cement sample, which is 58.6 seconds. Rho is the density. We know by the density of a cement is 3.1. Eta is the air viscosity at 20 degrees Celsius, which is 0.00015. Tetra 01819. So in this way you can calculate the specific surface area of a cement. This formula is taken from the ASTM standard, which I'll be. You have to make sure that you have calculated the surface area and then take the average of a 2, so that the results must be accurate. So what are the steps? What are the calculation steps that you can calculate, by which you can calculate the surface area of your specimen? First, you have to calculate the volume of this column in which the cement is inserted first, which can easily be calculated by means of some vernier caliper. You will first measure the length of this cell minus the length of this plunger, which is used to be inserted in this cell. You will minus these values to get the height of this column. So if we look at it, it's a circular shape. So it's you have to calculate its inner cross-sectional area, which would then be multiplied by the height of this cement column. So here it is pi d square by 2 is basically calculation of its cross-sectional area multiplied by J minus F. J is basically height between this point and this point. J is between the height between this and this point, and F is basically a length of the plunger between which is used to be inserted in cell, which is the height between this point and this. So we will get the height of column. By using this formula, we can calculate the volume of a cement present in it, so of a sample present in it. Then secondly, you will determine the mass required to be filled in that volume. So this is a formula, you can calculate it. E is basically the porosity of a specimen, rho is the density, V is the volume which I have earlier calculated. So here's come 2.56 grams of standard specimen would be used to calculate its time lag. Then you will this much amount of a specimen will be used in this column. In order to calculate the T naught, you will calculate the T naught, which is the time lag between point 2 and 3. After T naught comes, you will calculate the K, which is the constant of this for this device and standard specimen, for which you will be needing the specific surface area of that specimen, standard specimen, density of a standard specimen, porosity, and time lag. Eta naught is basically the density in air. By calculating K, you will have a value of 18.16. Then you will comes to your cement specimen, which you decide to calculate its specific area. So because of the reason that it has a different density than the standard one, you will calculate again the mass of a cement. Uh, you will compute the density, volume, and porosity of a cement to calculate the mass required. So 2.74 would be the mass used to be compacted in this cement column. So after the calculation, after the repetition of this experiment, you will after the repetition of this experiment, you will get the T naught. After the repetition of experiment, you will get the T naught T, which is the time between the mercury column, time between the manometric fluid column in the 2.2 and 0.3. It comes as 58.64. You'll compute it over here. You will calculate the specific area. By this formula, this is a formula which we have in ASTM standard. By repeating this procedure 2 times, you will take the average of two values. Then you will have an accurate surface area of a cement specimen. You can see that this S1 formula used for the calculation of a cement contains the K and the whole formula used. So in ASTM, what we have, ASTM 204, basically we have a formula of this. This is the formula to calculate the specific density of a cement. Yes, specific surface area of a cement. It has basically the surface area of a standard specimen, density of a cement specimen, um, uh, viscosity of a air, void ratio, different time for standard time of a your cement specimen. This formula is basically the same as that of I have used over here. Because this formula is split into two, we are using K before, then you compute the value of a K over here. So this is the same formula as specified in ASTM standard. So this is the ASTM 204 which we have followed for calculation of Blaine Air Permeability apparatus, for the calculation of surface area using Blaine Air Permeability apparatus. So in this ASTM reference standard, you will be needing all the accessories or equipment which we have used, including the Blaine Air Permeability apparatus, its cell, its plunger, its um, perforated disc. Then you have filter papers, This is basically the cross section. This is the cross section of your cell, and this is a cross section of a plunger. So you can see that this plunger just fit into this cell by keeping the volume of a cement or a specimen that you have, and after compacting the cement using this plunger, you will place this cell over the top of a UV manometer. So this is basically the cross section. Um, this is basically the calibration. Whole process is used for calibration that we have mentioned over here. This is the calibration step till step 5. After the step, you will get the after the calibration, you will get the K value. Is the apparatus constant. Using the K value, you will calculate the specific area of cement. So now we will discuss the different implications and different interpretations of these results. Um, Interpretations are basically the higher the time lag between the drop, higher would be the surface area. Uh, the main concept is the higher the surface area would be, the smaller would be the particle size, and the lesser will be the porosity. And it's very difficult for the air which is being entrapped in the U2 manometer to leave through the cell because of a higher surface area and lower porosity. So porosity and surface area are both interlinked. Lesser would be the surface area, lower with the higher would be the porosity, and it would be easy for the air to leave the cell. So second implication is higher would be the surface area, higher would be the reactivity, and higher reactivity of a cement can be expected. So lower surface area of cement uh, not are not desired to be used in construction because the surface area is basically corresponds toward the freshness of a cement. Higher the surface area, higher would be the reactivity, efficiency, and freshness of cement would be. If the surface area of a cement is too low, it means that the hydration has already been occurred. Then the efficiency cement would not be hydrate, as it have to be hydrate. The hydration reaction is previously occurred. Hydration reaction has already been occurred due to the reason that the cement particle sizes become larger. So in case of a lower fineness, lower surface area, um, we have a cement particle size larger than the standard cement particle size. Cement particle size is basically average particle size of a cement is around 30 micron. Here I have taken the cement particle size, a typical cement particle size, which is around 10 to 12 micron of a larger dimension. So it's basically a particle size of cement, which is being centered and grounded into finer particle size. It is unhydrated particle size. After the hydration is a process in which you mix the water, the reaction starts. The, the, the formation of hydrates is begin after the water is added. So if you add the water over here at 0 days, you will have the microstructure like this. After 12 days, you will have a microstructure which, with the same magnification, you can see that the particle size is too much higher than this one. So this slide is basically to make you understand how the cement hydrates and how the hydration products expands during the hydration. Um, on the other hand, you can see that the cement particle size over here is too much smaller. After the 12 days, you have a particle size of hydration products are too high. Basically, when the cement bag is exposed to some moisture, it gain the moisture and start to hydrating by by agglomeration of cement particles among each other to form larger particles. So hydrated or partial hydrated cement represents the lower fineness value. So it is important that before you execute your project, you must check the fineness of the cement so that its must be um, quality must be sustained. After the hydration, these are basically the hydration products in just one image. There are basically the three hydration product majorly forms in during the hydration reaction. This is basically the ettringite, calcium silicate hydrate, and calcium hydroxide. These hydration product I have already explained it very comprehensively in my lecture of cement production and cement production. So you can go there and see my lecture in which I have explained the ettringite, calcium silicate hydrate, and calcium hydroxide formation, how they are formed, and what they represent. So the fineness, the bottom line of this lecture is basically the higher the fineness would be, higher would be the reactivity. Lower the fineness mean the it might be due to the some storage issue. You have humidity at a storage of a cement in which it gains the humidity and start reacting before the bag was open. So uh, it can cause the quality issues in construction, and it can hinder to achieve the desired strength of a cement. Thank you so much for watching this video.